We've done the calculations for a strong acid with a strong base where the volume didn't change as we added base. We did the calculation for a weak acid with a strong base as the volume didn't change with the addition of the base. Then I went back and did this calculation where we saw that adding the base changed the volume, which is more realistic. In a real titration, you're usually adding a solution, so volume's changing. And that just makes more work in the calculation, the same basic calculations. We did the calculation strong acid, and now we need to do weak acid. And you'll notice I'm just rehashing what we had before. HI is a strong acid, HF is not. So here's how we were going to turn this problem into a problem where we're dealing with a weak acid instead of a strong acid. So what else isn't going to change? Well, as you may recall for the constant volume problems, our stoichiometry is not going to change. These are our mole numbers all the way through. And again, as you may recall from the other video, 1 liter 0.2 molar, that gives us 0.2 moles, and then we're adding 500 milliliter aliquots, 500 milliliter portions of this NaOH, which means we're adding 0.05 moles at a time. So all of that math is the same. The big difference, as you saw 2 videos ago, was that now the volume's changing. We start with 1 liter, and then we're adding 500 milliliters at a time. So in order to get our 0.05 mole change of our base, we need to add 500 mils of that 0.1 molar NaOH. So that is everything that was different from the constant volume to the not constant volume. And now we need to see how the calculations change. It was convenient for the strong acid because all we had to do was take into consideration how that total volume changed as the problem went. But now, with our weak acid, we've got to worry about ice and how that changes. And there's good news and there's bad news. I'm going to sneak in a spoiler alert here real quickly just to say when we get to the end of this calculation, all of these numbers are going to be the same as they were for our volume changing strong acid problem because it's the same total volume and the same excess amount of hydroxide. Our pH at this step isn't going to change from our previous weak acid problem because it's still in 1 liter. These numbers aren't going to change because it's a buffer solution and something special happens. This number is going to increase from here because it is a weak base solution, but it's not going to increase as much as it did from the previous video. We had that at 8.22 and it's going to drop down to 7.98. It's more dilute, the solution is going to be less basic. All right, back to all the actual work. So I've set this up in advance. We're going to be doing ice. When we have excess strong base, we've already established that those calculations are just going to be 14 plus the log of the moles of OH minus over the total volume. In fact, why don't we just copy those numbers over right now and save ourselves some time. One of them, we have 12.155, and again, that calculation is just 14 plus the log of our moles of OH minus over our volume total. All right, and those volume totals I have under that piece of paper right now. These numbers are the same as we saw for the strong acid problem because it's still excess base, excess strong base, and it's still in those same volumes, the way the problem's been set up. 12.398, 12.523, and 12.602. All right, no new work needed there. That saves us a little time. We're going to take a look then at these 3 cases last, and we'll look at this and this first because they, as you may recall from last time, involved some ice calculations. In fact, at the time, those ice calculations were based on this aqueous dissociation. And they are again, but we can't use 0.2 for this step. We need to use 0.2 divided by our total volume. Well, it's 0.2, but you get the idea. 0.15 now becomes 0.15 divided by the final volume. So I'll write this one out, and then I'll probably pause it and fill in the other blanks. Our HF we're going to do as a concentration, and that's going to be our 0.2 moles divided by our 1 liter. 0.2 moles over 1 liter, right? We know how things are going to change because we've seen that before. That change is going to be going down by x because we're dealing with a weak acid in this case. This will go up by x, and this will go up by x, and you end up with 0.2 over 1 minus x, x, and x. And the reality is we did that work before because it was in 1 liter when we used 2 moles before, it's going to be the same now. We can write our Ka equation again. Ka H3O plus F minus over HA, sorry, HF. And we know that's 7.2 times 10 to the minus 4. And then when we do this calculation, we just plug in x and 0.2 minus x squared over 0.2 minus x, which gives us an x value of 1.2 times 10 to the minus 2, and resulting pH as the negative log of x, that is 1.934. In fact, I'll just write that in a different color. pH 1.934. All right, same as before, because before it was in 1 liter. That's the same. Now when things change here, there's good news, and then down here there's the exact same bad news we had last time. What we have here is a situation where all of the HA has been used up, all of the OH minus has been used up, but now it's in 3 liters. So instead of doing that ice problem as we did here, where we said that the F minus was 0.20, now we're going to have to deal with that F minus as 0.20 over our total volume at that point, which is 3 liters. We don't have any HF, so this is an ice problem again, but we're going to have to work it from the fluoride aqueous dissociation. We did that in the previous video, and I just copied the work over right here for us, and we can set it up. We have this time 0.20 moles once again, but this time it's in 3 liters. All right, that gets us our molarity. None of that, 10 to the minus 7th from autoionization. We're going to lose some unknown amount and then gain that same amount on the other side, so we get 0.2 over 3 minus x, and x. And then we plug that in over here, x squared over 0.2 over 3 minus x, and we get a concentration there, x equals 9.63 times 10 to the minus 7. Oops, 9.63, 10 to the minus 7th. And that is our concentration OH minus. To get a pH, then, we're going to have to do 14 minus the negative log of that value, which is x. We'll just write it as. And we end up here with this pH equal to 7.98. And I'll write that over here, and we can cover that back up. All right, so our pH here, 7.98. And that leaves these 3. And I saved them for last, and I've been jumping around them, but this is where the Henderson-Hasselbalch equation really saves us some effort. And we did Henderson-Hasselbalch. In a buffer situation, you've got some amount of your weak acid or base and its conjugate, some amount of your weak acid or base and its conjugate, some amount of your weak acid or base and its conjugate. And right here we have that same situation. And I'm going to write in those volumes, but we're not going to need them. So thank goodness for small blessings. In this case, we're looking at 0.15 moles of HA, right? And that's over 1.5 liters. And then we've got 0.05 for our fluoride over 1.5 liters. And then just to fill these in real quickly, I've got 0.10 over 2 liters, that's moles, and 0.10 over 2 liters, that's moles, and then 0.05 moles over 2 liters, and 0.15 moles, 2.5 liters. All right, so those are our values, and we could do ice on those and work them through, but we said for a buffer situation, Henderson-Hasselbalch is a pretty good way to go. So I'm going to get a clean part of the paper here, and we'll do that calculation. The Henderson-Hasselbalch equation, which we derived in the original buffer video, just relates the pH to the pK of the acid and the ratio of the acid or base and its conjugate. And it turns out that pH is pKa plus the log of A minus over HA. All right, in this case, that's F minus over HF. All right, and we've got these HF and these F minus numbers. Now, you'll notice I don't put concentration there. Technically, those are concentrations, but take a look at what happens here. For HF, our pKa, and negative log of Ka, our pKa ended up 3.14, plus the log. And if I plug in the numbers I have here, like 0.05 over 1.5, over 0.15 over 1.5, the volumes cancel out. So this is the same thing as saying 3.14 plus the log of 0.05 over 0.15. And if we look back at the work we had done previously, when we did Henderson Hasselbalch, it was 3.14 plus the log of 0.05 over 0.15. In short, same numbers. All right. So Henderson Hasselbalch takes out this gratuitous step of having to factor the volumes back in, and that's nice. In fact, like if you could internalize some very, very important words, volume changes do not affect the pH of a buffer solution. And that, my friends, is very, very important. So we had these volumes changing and changing and changing, but for the buffer region, those volumes cancel out when we calculate that ratio. So it turns out it doesn't matter. And then these numbers are the same ones that we had before. And we can fill those in. From our Henderson Hasselbalch, we had 2.666. And 3.142 and 3.620. And you could do ice, you could turn those moles and volumes into molarities, but whatever. Henderson Hasselbalch is so much more convenient for that. And just now let's take a look at how things changed. The initial pH stayed the same, 1.394, because it was 0.2 moles in 1 liter, just like in the first example problem. Same because it's a buffer, same because it's a buffer, same because it's a buffer. pH went down. It's not as basic because the solution is more dilute. And then 12.699, we have the same situation where all of these pHs in the diluted solution where we had a volume for our base ended up lower pH. They're not as basic because the solution has been diluted. So again, exact same math we did, exact same stoichiometry we did. The only difference is you need to factor in those volumes, and in this particular case, the only place where we had to factor in those volumes was the first step and then that middle equivalence point step, and everything else stayed the same.